Okay, let's continue the discussion for the plane strain problems. And the first difference will be the D matrix. Okay, since we have different consider the strains and the straits, therefore the corresponding D matrix will be different. So either you can derive it by yourself, or you can check this from any textbook. If you can find the corresponding D matrix for the plane strain problems, then you can use it. But however, you need to understand how can we derive the D matrix. At least for the first time, you can derive it by yourself. Then you can use the table, the results. Okay, so after we know how to calculate the D matrix, then the next things we need to calculate the strain energy of the considered problems. And let's say we have changed it to the integration in the masked element, and we have the 1/2. There's a U transpose in the outside, and we have the Jacobian. Okay, and also we need to multiply the U vector. Okay, so that's the, actually there is one term. It is different from the plane strain element. So this term is okay. So when we calculate the strain energy of the plane strain problems, and remember, whenever we calculate the strain energy, we need to integrate over the entire volume. Even in this derivation, we consider the strain energy for a typical element. So that's the strain energy for only one element. It is not the strain energy for the entire structure. Okay, so remember the epsilon is equal to the B times U, and if we need an epsilon transpose, so we need to change it to the U transpose and multiply by the B transpose, and also we need to multiply the strains inside the structure. The strains is equal to the D matrix multiplied by the strains. The D matrix multiplied by the strain, and the strains inside the element, it is also the B matrix multiplied by the U vector. Okay, then why we have the Jacobian? Remember the Jacobian multiplied by the D Cassini and the D eta. It is since the Jacobian is the ratio of the area in the real element divided by the area in the masked element. So the D Cassini and the D eta, multiply them together, it represents the area in the masked element. If we multiply these two terms by the Jacobian, then we can get the dx times dy, or the d area. Okay. Why we need to multiply a t in the plane strain problems? Since we need to calculate the strain energy for this element, and for the plane strain problems, it is thin plate. The thickness is a relatively small dimension compared to the dimensions on the x and y plane. But we still have the thickness t. So if we need to calculate the volume for this small element, it will be the Jacobian times d cosine the d eta. It will give you the d area. And the d area times the thickness of the thin plate. Then you can get the d volume. Then you can get it. So for the plane stress problems, we need to multiply the t when we calculate the strain energy. But remember, for the plane strain problems, the dimension perpendicular to the xy plane, it is infinity. The dimension along the z direction. Okay, excuse me. So remember the dimension along the z direction, which is an infinity in the assumption for the plane strain problems. The dimension along the z direction, which is close to infinity. So if we need to calculate the strain energy in even it is a single element, since you can say the thickness is close to infinity. So the volume, it must be infinity. So there is no way you can calculate something which the volume which is infinity. There is no way we can calculate this. But for the plane strain problems, usually we just take the thickness of 1. Okay, so although the thickness along the z direction, which is close to infinity, but we just take out a unit thickness. Okay, so we just calculate the strain energy for a unit thickness along the z direction. So the 1 represent okay, so we will use the value of 1 instead of the t. Okay, that's another difference between the plane strain problems and the plane stress problems. When we calculate the strain energy, you need to consider a unit length along the z direction. Okay, so although you can choose 2 or 3, but no matter which one you choose, when you calculate the strain energy, if you choose a unit length, then when you calculate the V, okay, if you choose a unit length to calculate the strain energy, also you need to choose a unit length when you calculate the V, the potential energy due to the applied loading. Okay, so when you calculate the P value, the P vector, okay. Also, when you calculate the P vector, it will be the results from a unit length along the z direction. Okay, so if that's the shape of the structure, if we consider the distributed loadings applied on the top of the structure, when you calculate the resultant load, you need to multiply the density of the distribution loadings by the length on the xy plane. Also, you need to multiply the thickness, and or you can say the considered density, which is obtained from a unit length along the z direction. Okay, so if the u is considered for unit thickness along the z direction, when you consider the applied loadings, they will be also a unit length. Okay, so if we consider a concentrated load, and the concentrated load will be the concentrated load will be the loadings applied, the loading, resultant loading obtained from a unit length along the z. Okay, so all the terms related to the thickness, they will be the same value. Then you can get the correct result. And the choice of 1 is not the only possibility. You can also choose the thickness to be the 2 or 3, but most of the time we just choose the 1. Okay, so actually, if you compare the plane stress problem and the plane stress problem, actually there are only so far there are only 2 differences. The first difference is the D matrix. The second difference is the thickness we need to calculate. No matter when we calculate the strain energy U or the V, the potential energy due to the applied loadings. When we output the results, we need to output the nodal displacements. They are exactly the same for both models. And when we output the strains and the stress for each element, for the plane stress problems, you can output the 3 non-zero stress, but you can output the epsilon z, the fourth non-zero strain. That's the epsilon z. For the plane stress problems, you can output the 3 stress and the 4 strains. But for the plane strain problems, you can output 3 non-zero stress. You can output 4 non-zero stress, include sigma z, and also you can output the 3 non-zero strains, the 3 strains. Okay, so for this model, I will not repeat the procedure since the almost all the procedure they are same as the plane stress problems. But remember, what are the difference points between these 2 models? And if you know how to solve the plane stress problems, and you know what are the difference for the plane strain models compared to the plane stress models, then you can say you can solve both problems. Okay, take the picture and I will continue. Then I will go to the next topic, and you can say that's the next type of the problems or the next type of the elements we can consider. The next problems will be the axisymmetric problem. Or you can say okay, we will derive the axisymmetric elements. The axisymmetric elements, they are derived to solve the axisymmetric problems. Okay, first you need to understand what kind of the problems they are the axisymmetric problems. And why we call this type of problems, which is the axisymmetric. You can say we have a type of the structural model, and the name of the structural model, which is the axisymmetric model. Okay, the axisymmetric model, which is also a three-dimensional structure, but there is some very special case. Okay, usually we will call the two axes, the axisymmetric problems. It is also a two-dimensional problems. So it means we can use only a set of we can use two coordinate systems and to describe the geometry, to describe the applied loadings, and also we can use only these two coordinates to describe the obtained displacement or anything. Okay, so the axisymmetric problems, we use two coordinates. Usually we name these two by first, which is the r-axis. The second is called the z-axis. And this type of the coordinate system, sometimes it is called the cylindrical. Okay, so the coordinate system obtained for a cylinder. Why it is a cylinder? And the z-axis, also it is you can say it is a three-dimensional structure. And if we see the geometry on the RZ plane, then we will make a rotation. We will make a rotation, and this rotation is rotate about the z-axis. So the z-axis, it is also okay, which is we will rotate the structure, we will rotate the applied loadings. Everything will be rotated to get the entire three-dimensional structure. Okay, so although we see just it is only a plane structure. Right now it is a plane structure. But what is the entire three-dimensional structure? The entire three-dimensional structure can be obtained by this plane structure. Rotate it about the z-axis. Okay, so if the structure which is a circle, then what is the entire structure? Okay, so the entire structure will be this circle, this circular area, rotate about the z-axis, then you can see something looks like a donut. Okay, I believe all of you eat the donut before. Okay, it is sprayed the sugar on the top, and that's the donut. Okay, let me write the Chinese character. Okay, so that's the name of the Chinese. So if you are a foreign student, if you like to eat a donut in a fast food restaurant, you can say, I like to eat the Tian Tian Quan. Okay, so the Tian Tian Quan they will give you the donut. Okay, so just imagine a circular area on the RZ plane. It represents a three-dimensional donut. Okay, it is something like a donut. Okay, not only the geometry of the structure can be obtained by the rotation about the z-axis, also the applied loadings. Okay, if we see the loads, they are applied to the RZ axis, then all the same loadings will be applied to all the three-dimensional structures. So if you cut any plane, the cut plane which is start from the z-axis and along any radial directions from the center of the z-axis, you will see exactly same geometry of the structure. You will see the same applied loadings. Also, you will see the same boundary conditions. Okay. So it means the loading. Okay, all these three, they will be same. The geometry, the applied loadings, the boundary conditions. So if we take a top view, okay, so if we take a top view, then that's one of the RZ plane. Okay, and sometimes we will call why it is named R-axis. Sometimes it is said that that's the radial direction. The R represents the radial direction. It starts from the rotation axis. It starts from the z-axis and goes to the outside. So sometimes we will use the theta. The R-axis can be defined for any theta. Okay, so no matter the values of the rotation angle from one of the radial direction, if we change the angle theta, and then you can define another RZ plane, and you can see exactly same geometry, exactly same loadings, exactly same boundary conditions. Okay, so that's the axis symmetric. And also remember the all the structural model, they have the simplified assumptions. In the real structures, it is very hard to find anything which is exactly same as the assumptions of the structural model. It is always have something there is a little bit different from the real structure and the structural model. Okay, so that's the first you need to understand what is the axisymmetric problems, what is the axisymmetric structural model, and then let's discuss what kind of the finite elements which can be used to solve problems like the axisymmetric problems. Okay, it's time for you to take the picture. Okay, it is similar to the plane stream problems. The displacement has got some special character. Since we have assumed, for example, for the plane stream problems, the dimension along the z direction, which is close to infinity. Therefore, we cannot expect any displacement along the z direction. If for the axisymmetric problems, let's take a top view, and let's consider the donut. Okay, the circle is not very accurate. However, it should be a circle, and it is outside radius, and there's the inside radius, and actually it is a circle surrounded. Okay, it is a top view of the structure. Okay, so actually we observe the structure from the positive z direction. So we just observe the structure from the top. Okay, that's that's the structure we see, and let's assume we have the loadings applied from inside to the outside. Okay, and for the axisymmetric structural model, the distributive loading must be same. You cannot solve the axisymmetric problems. You have the larger distributive loadings, for example, at the 12 o'clock direction, but you have smaller distributive loading at the 6 o'clock direction. Okay, it cannot happen for the axisymmetric problems. Based on the assumption of the structural model, the applied loading must be same, no matter which direction you consider. No matter 12 o'clock, 6 o'clock, 3, 9, any direction, the loading must be same. The loading must be same. Okay, if a structure and the applied loadings, they can fulfill the axisymmetric problems, then what kind of the displacement we can get for any point in the structures? Any point inside the structure. Okay, for any point inside the structure, for this point, it must the displacement of this point, it must be on the RZ plane. Okay, the only non okay. So remember, the theta is the rotation angle from one axis. The theta is unchanged. No matter the theta, if you define the theta from the top view, no matter the angle of the theta, everything is the same. So you cannot expect the displacement which is along the theta directions. So it means the displacement, the tangential displacement perpendicular to the RZ direction. Okay, so there is no you can, since every theta is the same, so you can use the similar logic to explain why the displacement should not have the direction along the theta direction. The only non-zero displacement must be along the either along the R direction or along the Z directions, or you can have both components, they are non-zeros. So you have a combined direction on the RZ plane. Okay. It is such kind of the conclusions. They are also come from the basic assumptions of our structure model. Okay, so only the displacement must be on the RZ plane, but there is since all three structure models, they are different. The plane stress and the plane strain problems, the strains and the stress along the Z directions, we have either one which is the non-zero, but the corresponding terms it is equal to 0. But for the axisymmetric problems, if we have axisymmetric structures subjected to the pressures from the inside of the donut applied to the structures, you can expect the displacement will be something like this one. Okay, so you can expect the expansion of the donut. So it can change it from a small radius to a larger radius, or the diameter which is become large, since the applied loading which is starts from the inside of the circle and apply it to the, so that's the deformation of the structures. Although we have the expansion of the circle, but the points, this one is moved to the outside, this one moved to the outside. All the points, they should move along the R direction, or either sometimes combine of the displacement have the components along the R, and sometimes also it has the non-zero component along the Z direction. But any point inside the structure, it must move only on the RZ plane, Okay, so the displacement will have only non-zero components on the RZ plane. But if we consider a three-dimensional orthogonal coordinate system, one is the R direction, one is the Z direction. The third direction will be perpendicular to the RZ direction, or you can say it is the theta direction. Okay, and the theta direction, you can say it is the third component of an orthogonal coordinate system. For the structure like this one, the orthogonal coordinate system, especially for the r-axis and the theta axis, they can change. They are not a constant, and for different point we have different r and theta direction. But the z axis, it is always the same. But for different point considered, we have the r theta axis, which is defined only for this point. Okay, and the displacement along the z direction, along the theta direction, it is always equal to 0. But for a structure like this one, you will find the displacement along the displacement along the theta direction, it is always equal to 0. But do we have the non-zero strain, the epsilon theta? You can see the radius of the structures. That's the original structure, the blue color, which is the deformed structures. So you can see a bigger, right now the structure shape has a bigger radius, or you can say we have a bigger diameter. Okay, since it changed from a small circle to a much larger circle. So you should expect we have the epsilon. Okay, we have the epsilon along the theta direction. So the epsilon theta is not equal to 0. Also, if we have a structure like this one, you can expect also we have the tensile stress, since the original shape it could be in the relaxed mode. But if we expand the small circle to a much larger circle, then you can expect there is the stress along the theta direction. It should be a tensile stress. Okay, so not only the epsilon theta is not equal to 0, also the sigma theta it is also non-zero. Okay, that's the typical points for the axisymmetric problems. We have 0 displacement along the theta direction. We have non-zero strain, epsilon theta, it is non-zero. Also, the sigma theta is also non-zero. If both epsilon and the sigma, both the strain and the stress, they are non-zeros, then you can expect when we calculate the strain energy of the structure, you need to consider the contributions from the epsilon theta and the sigma theta, since both of them, they are non-zeros. Okay, so they will contribute to the strain energy of this structure. Okay. Okay, I think I will take an early break, so I will continue this to the next hour.